The way I have explained the time reversible concept in the DTMC, the CTMC also has the time reversible concept. So, the time reversibility equation is a pi I is equal pi I times q I j is equal to pi j times q j I. The q's are nothing but the rates and the pi's are nothing but the probability values. So, if pi i's exist, if pi i's exist, this stationary probability or stationary distribution exist, then if the stationary distribution exists as well as the time reversibility is satisfied by CTMC, then that CTMC is a positive recurrent, and you can say that it is a time reversible, and the solution pi can be, pi is nothing but the stationary distribution. So, this result says for irreducible CTMC, if there exists a probability solution pi satisfy the time reversibility equation. This is a time reversibility equation where q's are rates, pi's are the probability solution. If it is satisfied by the irreducible CTMC, the time reversible equation, then that CTMC has a positive recurrent states, and that CTMC is called the time reversible, as well as the pi is called the stationary distribution. So, initially we have not taken as a stationary distribution, some probability solution satisfies the time reversibility equations and it is a irreducible CTMC, then that CTMC has a positive recurrent states and the pi is nothing but the unique stationary distribution. So, the usage of this concept is whenever any CTMC is first it is irreducible and satisfies the time reversibility equation of this form, then you do not want to solve pi q is equal to 0 and the summation of pi a is equal to 1 to get the stationary distribution. Instead of that, use this time reversibility equation instead of solving pi q is equal to 0, and then use a summation of a pi a is equal to 1 to get the one unknown. That means use the time reversibility equation repeatedly, recursively, and get all these in terms of one unknown, either pi naught or pi 1, whatever it is. Then use the summation of pi a is equal to 1 to find that unknown instead of solving pi q is equal to 0. So, whenever it is model is irreducible and time reversibility equations are satisfied, then you can conclude all the states are positive recurrent and you can find pi the stationary distribution in an easy way instead of solving pi q is equal to 0. I am going to give one simple example what is the limiting and stationary distribution. Take the two state CTMC and we know that Q matrix, and you can verify whether this is going to be irreducible and a positive recurrent, since it is a finite state model and both the states are communicating each other. Therefore, it is a irreducible positive recurrent states. So, you can solve pi q is equal to 0 and the summation of pi a is equal to 1. So, pi times q, pi is the vector, q is the matrix and again 0. Therefore, if I take the first equation, I will get minus mu times pi naught plus pi lambda times pi 1 is equal to 0 by taking the first equation, minus mu pi naught plus lambda times pi 1, that is equal to 0. From this I can get the pi 1 in terms of pi naught. Since it is a homogeneous equation, I have to use a non-homogeneous or normalizing condition, summation of pi a is equal to 1. So, using that I will get pi naught is equal to lambda divided by lambda plus mu. Once I know pi naught, then pi 1 is equal to mu divided by lambda plus mu. So, this is the stationary distribution as well as the limiting distribution, because it satisfies both the conditions. Take the second example. Second example also finite state model. All the states are communicating with all other states. Therefore, it is a irreducible. Since it is a finite state model, you won't have a null recurrent, it's a positive recurrent model. So I can solve pi q is equal to 0 and the summation of pi a is equal to 1. So there are 3 equations. So I take the first 2 equation and one normalizing equation and solve these 3 equation, I can get pi 1, pi 2, pi 3. You can verify that the summation is going to be 1. So this is the limiting distribution as well as the stationary distribution, because the model is the irreducible positive recurrent model. So this limiting distribution and the stationary distributions are one and the same. Instead of solving pi q is equal to 0, you can use the time reversibility, but before that we should verify whether the time reversibility equations are satisfied by this model. If this model satisfies the time reversibility equation for all I, comma j, then you can conclude it is a time reversible Markov chain and so on. But example 1 is a time reversible Markov chain, whereas that example 2 is not a time reversible Markov chain. You can verify it. Now I am moving into the special case of a continuous time Markov chain, that is a birth death process. This is a very important time homogeneous continuous time Markov chain, because many of the scenario can be mapped with the birth death process, either with the finite state or infinite state. Let me first give the definition of a birth death process. I started with a continuous time Markov chain, that is a time homogeneous continuous time Markov chain with the state space countably infinite. It can be a finite also. That CTMC is going to be call it as a birth death process if there exists a constants lambda i's and mu i's such that, and these are all nothing but the infinitesimal generator matrix elements, and this is I to I plus 1, that rate is always lambda I, and the rate in which the system is moving from the state I to I minus 1, that rate is mu I, and the diagonal elements are minus of lambda I plus mu I. Whereas all the other rates, the system is moving from the state I to j other than I to I plus 1, I to I minus 1 and I to I, and all other rates are always 0. Absolute of I minus j is greater than 1. That means you will have the infinitesimal generator matrix in which you will have only have a diagonal matrix, tridiagonal matrix, and all other elements are going to be 0. I can write down the condition so that it land up the rates are going to be only lambda i's and mu i's, so on, not all other rates are going to be 0. So if I start with I is equal to 0, the system is moving from the state 1 to 0 in the interval of delta t, because it is a time homogeneous model. So this is nothing but this probability, the system is moving from the state 1 to 0 in the interval of delta t, that is nothing but the rate is mu 1 times delta t plus order of delta t. Similarly, the system is moving from the state 0 to 0 from the time t to t plus delta t, or during the interval delta t, that is nothing but 1 minus lambda naught times delta t plus order of delta t. So these mu i's and the lambda naught and so on, these values are always going to be greater than or equal to 0, strictly greater than 0 also. For I is greater than 0, the system is moving from the state I to I, that is 1 minus lambda I times delta t minus mu I times delta t plus order of delta t, whereas the system is moving from I plus 1 to I, one step backward, that is mu I plus 1 delta t. The system is moving from the state I minus 1 to I for I is greater than 0, that is a forward one step move, that is lambda times I minus 1 delta t plus order of delta t. this order of delta t, it may be a function of delta t, it need not be the same. As delta t tends to 0, these quantities are going to be 0. Order of delta t divided by delta t is going to be 0. Therefore, this is the way the system is moving from the one state to either one step forward or either one step backward or move anywhere. So, these are all the only 3 possibilities with these probabilities. Therefore, we will end up the Q matrix is going to be the system is moving from the state I to I plus 1 forward one move, that rate is lambda i's, and the system is moving from the I to I minus 1 one step backward, that is mu I, or the system being in the same state, that rate is minus lambda I plus mu I. Therefore, there is no other move from the system from one state to all other states, either one step forward or one step backward. So, this can be visualized in the state transition diagram. Since I started with the state space 0 to infinity, there is a possibility you can have a label from some negative integers to the positive integers. So, you can always transform into something. Therefore, default scenario or the simplest one I discussed from 0 to infinity. Therefore, you can visualize whatever be the label that can be transferred in a one-to-one fashion. So, this is the rate in which the system is moving from the state 0 to 1, that rate is lambda naught. The system is moving from the state 1 to 2, that rate is lambda 1, or the system is moving from the state 1 to 0, that rate is mu 1. Therefore, the time spent in the state 1 before moving into any other states, that is a minimum of the time spending in the state 1 before moving into the state 2, or the system time spending in the state 1 before moving into the state 0. So, both are exponentially distributed with the parameters lambda 1 and mu 1, and the minimum of that time is the spending time or the waiting time in the state 1, that is going to be exponential distribution with the parameter lambda 1 plus mu 1, because both are independent. The time spending in the state 1 before moving into the state 2, and similarly the time spending in the state 1 before moving into the state 0, and both the random variables are independent, that is assumption. Therefore, it is going to be a exponentially distributed random variable, the time spending in the state 1, that is exponential distributed with the parameter lambda 1 plus mu 1. Like that you can discuss for all other states. So, whenever you have a birth death process, the system either move one step forward or one step backward, then it is called a birth death process. Therefore, here these lambda i's are called the system is moving from one state to forward one step. Therefore, these lambda i's are called the birth rates. The system is moving from one state to the previous one state, and the corresponding rates mu i's, mu 1, mu 2, mu 3 and so on, and these rates are going to be called it as a death rates. So, lambda i's are nothing but the birth rates. That means the rate in which the system is moving from the state I to I plus 1, that depends on I. Therefore, that rate is lambda I. The system is moving from the state I to I minus 1, that is related to the death by 1, that is a function of I. Therefore, that death rate is mu I. So, the lambda i's are the birth rates and the mu i's are the death rates. Therefore, this is suppose example, the system moving from the state 2 to 1, the death rate will be mu suffix 2. So, you can fill up the Q matrix. If you see the Q matrix, it is a tridiagonal matrix. So, here I am giving few examples for the birth death process. The first example consists of the first example is a finite state model. The birth rates are lambda naught, lambda 1 till lambda n minus 1. The death rates are mu 1, mu 2 and mu n. It is a finite state birth death process. The second example is the infinite state birth death process. The third example, all the death rates are 0, that is also possible. The fourth example, all the birth rates are 0, that is also possible. But you can discuss the one can discuss the state classification also. The first one, it is a finite state model, all the states are communicating with all other states, therefore, it is a irreducible positive recurrent birth death process. The second one, it is a infinite state, all the states are communicating with all other states, it is irreducible, but one cannot conclude without knowing the values about the lambda naughts and lambda i's and the mu i's, one cannot conclude it is a positive recurrent or null recurrent. If the mean recurrence time that is going to be a finite one, then you can conclude it is a positive recurrent, otherwise it is null recurrent. So, as such one cannot discuss now the positive recurrent or null recurrent, but you can conclude it is a recurrent state. The third example, the system is keep moving forward, therefore, all the states are transient states. It is not irreducible, it is a reducible model, all the states are transient states. That means, as a t tends to infinity, the system will be in the some infinite state. So, one cannot define an infinite state, therefore, the limiting distribution will not exist in this situation. The fourth example, it is a finite model, but all the states are not communicating with all other states, therefore, it is not a irreducible, it is a reducible model. Whenever the system starts from some state other than 0, over the time the system is keep moving backward, and once it reaches the state 0, it will be forever. Therefore, state 0 is the observing barrier,